In this second part of chapter 15, we will cover the topic of alternating current and voltages, but we're going to start with, we're going to start in section 15.9, which is phase angles. Okay, so phase angle is the angle between two different waveforms of the same frequency. So when we compare waveforms, we must make sure that they have the same frequency. So two waveforms that have the peaks and the zero values at the same time are in phase. In other words, they go through the same number of degrees at the same time. When one of the waves is at its peak value or the maximum value, and the other one at the same time is at the zero value, they're said to be at 90 degrees out of phase. So when they're in phase, remember, they go through zero and their maximum values at the same time. But when one goes to the maximum value while the other one is at zero, then they are 90 degrees out of phase. And when one is the exact opposite of the other one, basically what that means is that when they both go through zero at the same time, but when one is at its maximal value and the other one is at the minimum value, then they are 180 degrees out of phase. Let's take a look at this example. If we look at the sine wave A, the blue line, okay, this one starts at zero, goes to its maximum value, comes back to zero, then go back to its maximum negative value, and then goes back to zero. This is a complete cycle. This is the sine wave. The red wave is the cosine, which is the same as the sine wave, but is shifted by 90 degrees. So when the blue one, the wave A, is at zero, wave B is already at its maximum value, right? And then they just keeps going, and when this one is at its zero value, then A is at its maximum value. Then when this one goes to the maximum negative value, A is at its zero value, and so on. So this one goes to zero, then this one is at its max here, and when this is at its max value, this one is at zero. So these two waves are said to be 90 degrees out of phase. Okay? In other words, the wave B leads wave A by 90 degrees. This can also be represented on the diagram, a phase diagram, including these vector-like lines. They're called phasors. The difference between a vector and a phasor is that the vector is a measurement in space with a direction, and this one is with reference of time. The phasors are with reference of time. Okay, so in order for you to compare, you must have two waves, and you must select one as a reference. In this case, we're going to select the wave A as a reference. We place that on the horizontal line, and then counterclock, we're going to measure the phase angle. So between A and B, there is 90 degree difference, so this would be the representation of B. The magnitude of this phasor represents, the physical size of the phasor represents the magnitude of the wave, and the angle represents the difference, the phase angle between the two waves. Okay. We can take any one of the two waves as reference. On this case, I took A as a reference, and then because B is ahead of A, so it's going to be in the positive angle of 90 degrees. That's a representation of these two phasors for waves A and B. Now, if I want to take wave B as a reference, then I place wave B on the horizontal line, and then the difference in angle, because when B is leading A, we can also say that A is lagging A, so the angle is going to be in the negative direction here, clockwise direction, by 90 degrees. And now we can say that in this case we say that B is leading A by 90 degrees. In this case we say that A is lagging B by 90 degrees. The time factors for frequencies and in frequency and phase is the time that it takes for the waves to cover the difference, the difference in the angles. Okay, so basically, the way we calculate the time factor is by calculating the fraction of the whole revolution. Okay, the fraction of the whole cycle that is represented by that phase angle, and then multiply that times the period. Remember that the period is equals to 1 over the frequency. This can be replaced by t if we know the period of the wave, but if we know the frequency, then we say it's 1 over the frequency, which is the same thing as the period. So basically, this angle, the angle in the event, for example, of 90 degrees, if the angle is 90 degrees, will be 90 divided by 360, and that would be 1/4. So the time factor of this phase angle will be 1/4 of the total period. So 1/4 times the period, and that will give you the time factor. Okay. So remember, the time factor is the time that takes from here to here. Okay, when we compare the difference between the two waves in terms of time. Okay, so how long does it take for this 90 degree to happen? Okay, that is the time factor, and that is calculated by dividing the actual angle, the 90 degrees, divided by the whole cycle, which is 360 degrees, and that will give you what fraction of the whole cycle that 90 degree represents. So once you get that fraction, you just multiply that times the period, and that will give you the time factor of this angle, okay, of the phase angle. When we're working with alternating voltages or currents in a circuit that has only resistance, the alternating current has the same effect as the DC voltage. So therefore, the calculations that we used when we deal with DC voltages are used in the AC scenario as well, because the RMS value, remember, the values that are given to you on the source information of the problem, they're typically the RMS value, and the RMS value is the equivalent to a DC value. So when we have a circuit that has resistors only, okay, the elements on the circuits are the source and resistors only, we can use the same method that we use to solve problems with DC values. For example, on this one, we have two resistors in series. If we need to find, if we know that we applied 120 volts to this circuit, and we know the values of the resistors, they're in series, we can just add them up, and then divide the voltage by the total resistor. In this case will be 30, and that will give you 4 amps as current. Okay. Same happens if you have parallel circuits with resistors only. If you have 120 volts, you remember that when you're dealing with parallel circuits, the voltage across all the branches is the same. So these 120 volts are expressed right here on this branch and this branch. So we calculate the total resistor of this and then use the same methods that we use with DC voltage to calculate the current. In this event, the current will be 18. Okay? Remember, on parallel circuits, the voltage is the same across all branches, where the current is the sum of all currents of all branches. Okay? So let's assume that you have this node right here, and you have 18 amps coming into here. So these 18 amps must be split between these two branches. You get 12 here and 6 here. And you get more on this one because the resistor is bigger. Okay, so in parallel circuits, the voltage across all branches is the same. The current coming into the node have to be equals to the current coming out of the node. Okay. And I believe that we went over this, you guys went over this during the first 14 chapters of the book. But if you still have questions, please let me know. So same thing happens when you are doing a series parallel AC circuit with resistors only. Remember this, okay, resistors only. We calculate the total resistance, and then we use the Ohm's law to calculate the current and everything else. Alright, so let me go ahead and switch over here so I can show you this example on the in here. Okay, this is the same problem that was in the book. If you can see, alright, so here is the circuit, alright? So this is an alternating voltage that's being applied. Then you have a resistor 1, resistor 2, 10 and 20 ohms respectively. Because they're in series, you can add it and you can replace this thing by one big resistor that has 30 ohms. Okay, so divide 20 divided by the resistor, 120 divided by 30, that will give you 4, and that's the amperes on the current. So the current on this circuit will be 4 amps. However, because this source is an alternating voltage, the current that you're going to have through this circuit is also going to be alternating. So when the voltage is positive, for example, we're going to say that the current goes this way. When it passes the 0 and then goes to the negative section, then it reverses direction. So it keeps doing this over and over for every single cycle, because the waveform for the voltage will be the same waveform for the current, because they're in phase. Okay, so the star right here, let's say this is the voltage that's being applied, and this is the current that results from applying this voltage to the load. All right, so the voltage and the current on a resistive circuit are always in phase. They go through zeros at the same time, and they go through their peak values at the same time. Okay, that's what it means that they're in phase, that they go through zeros and their peak values at the same time. The amplitude, it can be different. The amplitude, it doesn't matter. They can have a one large and small amplitudes. That's not a big deal. Okay, as long as they go through their maximum values at the same time, so they're in phase. All right, then. Let me get back in here. Okay, there are other alternating voltages or currents also, that they're not necessarily be on a waveform. Represented by a waveform. You know, there's some examples that we see right here. This is the square wave. This could be also a voltage that can be applied to a circuit. This is another one, the sawtooth wave. It looks like this, and these are some of the typical uses for it. The pulse wave, that's another one. It's like it goes up, then goes down, stays down, goes back up, and keep doing this over and over. If you have this one, for example, you have a cycle that goes from here all the way to here. Okay, so from here to here is one cycle, because at this point it repeats again. Okay, on this one you can say that the cycle will be from here to here, and then it repeats over and over. On here you can say the cycle goes from here to here. All right, so these are different waveforms that they're used in different applications. Okay, and remember, the waveforms, it just tells you how is the voltage being applied to the circuit. And here are some similarities and differences. For all waveforms, the cycle is measured the same way, like I just explained on the previous slide. The peak amplitude is also measured from the zero axis to the maximum positive or the maximum negative value, just like the sine wave. And the peak-to-peak value will be measured on the same way. You go from the maximum positive all the way down to the maximum negative, and the difference between the two, that will be the peak-to-peak. Okay, for all sinusoidal or non-sinusoidal waveforms. Okay, now the RMS value, that applies only to sine waves. So if you have a square waveform that's being applied, you cannot calculate the RMS value there. Okay, so the RMS value that we discussed in class, and the ones that that we talked about in the previous video, is also it's good to remember that these only apply to sine waveforms. When you have an alternating voltage source that is in a sine wave, that's when you use the RMS value. Also, the phase angle only applies to sine waves. So you can have like square waves, that they come in at different times. So that right there, we cannot apply the phase angles to those kind of waves, only with the sine wave. So all the sine waves, all the waveforms represent AC voltages. Positive values are shown above the zero axis, and negative values are shown on below the axis. Another term that we need to learn during this AC section of the course is the term that's called harmonic frequencies. Now recall that what is the frequency? The frequency is the number of cycles that are completed in 1 second. Okay, that's the frequency, the number of cycles per second. Harmonic frequencies are multiples of this frequency, or the fundamental frequency. So, for example, if you have a waveform that has a frequency of 2 hertz, only 2 cycles for 1 second, and you multiply that wave times, let's say, 3, so you're gonna get 6 cycles per second. That would be the third harmonics. And they're useful when analyzing distorted sine wave or sinusoidal waves. Okay, a common unit of frequency multiples is the octave, and that is when you have a multiple of 2, basically. You double the frequency. Doubling the frequency, that is a multiple that is called the octave. For example, if you have something that runs at 200 hertz, and then you turn it into something that multiply times 2, and you get a new waveform that has 400 hertz, that would be an octave. Okay. Another one is that when you multiply this times 10, if you have a waveform that gives you 30 kilohertz, that means 30,000 cycles per second, you multiply that times 10, and you get a new waveform that has 300,000 cycles per second. That would be a decade. Okay, that's the name of this. The 10th multiple is decade. The second multiple would be a octave. Here's an example. The blue waveform is the fundamental waveform. In other words, the original waveform. The second one will be the one in red. This will be the third harmonic Well, what it means by third harmonic, that means that if this one, the fundamental, has only one cycle, okay, one cycle in this 100 seconds, okay, the fundamental will have the third harmonic will have 3 cycles in the same time. So from here you go 1, 2, 3, right? So basically the third harmonic is the fundamental times 3. The fifth harmonic is expressed on the yellow waveform here, okay? And it's the fifth harmonic. That means you take that and multiply that times 5 and you get 5 cycles for the same period of time, okay? The same length of time, you get 5 cycles in the same time that the harmonic was only 1 cycle, okay? Obviously the periods here are different. This is the period for the harmonic, for the fundamental. From here to here will be the period for the third harmonic, and from here to here will be the period for the fifth harmonic, okay? Fundamentals and harmonic frequency. For an example of 100 hertz is shown in this picture. Talking about AC power lines, like I explained in class and during the lab, that most of the most of the houses, all houses basically in the U.S. receive a alternating voltage between 115 and 125 volts RMS, and the frequency is at 60 hertz. Each cycle goes positive, negative 60 times per second. In some places outside the United States, in like Europe, for example, I believe that the frequency for the power lines for the electricity of the houses is 50 instead of 60. Okay. Here are some applications in residential wiring when it comes to power lines. So all residential wiring uses AC power instead of DC because AC is more efficient in distribution from the generating station. In other words, it is easier to transmit and distribute AC power than DC power. Typically, the houses in your house, the wiring in your house, we have 3 wires, single phase power, meaning that in some cases you're gonna see the outlet, that have three holes in it. One of those is ground, so it have to be ground for safety purposes. Okay. High voltage can supply power with less power losses. Okay, since the power is produced with less current. In other words, typically when on the power lines, the high voltage power lines outside the house, the electricity, the power is transmitted on those power lines at very high voltages. So because the power is the voltage times the current, all right? So if we need to transmit a lot of power, so we rather have high voltages and very little current on it, so to transmit power, because remember, the current is the one that generates the heat on the wire, and that heat is basically power loss. Some power gets dissipated in the lines if we put too much current in it. So what they do is they put a lot of voltage on it and very small current, so to transmit the power on the high voltage power lines. Okay, once you get to the transformers, and then it goes through a process, and then it's delivered to your house as 120, typically 120 volts AC. This is what I mentioned before. In North America, 60 hertz, but many places outside the U.S. they use 50 hertz. Latin American and Europe, I believe that they use 50 hertz. Okay. And there is always a little bit of tolerance, so it doesn't have to be exactly 60 hertz. Now, grounding, okay, it is very important when you're dealing with electricity, you have to have ground, because it's for safety purposes mostly. Grounding is the practice of connecting one side of the power line to earth ground. The purpose is safety. Grounding provides protection against dangerous electric shock. The power distribution lines are protected against excessive high voltage, particularly from lightning. So that's what the ground line does. Okay, so it protects the lines and also protects the people that is using it. So here you will see some different types of connections. So if you look at your appliances at your house, some of the appliances will have this type of connector. So this white one is the one that is connected to neutral, and the other one is this kind right here, where the round thing in here is the one that is connected to the round pin is the one that's connected to ground. Also, another safety feature that you can see around your house is the GFCI outlets. Okay, this one, they do have a safety feature in here that whenever they detect an excessive current, then it works like a breaker. They open the circuit so your house doesn't get on fire, or whatever you have connected in there doesn't get an excessive current through it, and it prevents you from getting shocked. Okay, this section of the chapter is more informational, more conceptual. So between the generator and the motor, but basically what you need to know is that the generators they convert mechanical energy into electric energy, like the one that we saw at the beginning of the chapter when we explained what the AC voltage was. When we have a magnet and we have the conductors, turning within the magnetic field, and the flux induces the voltage into the conductor, positive or negative voltage. Okay, so that is a generator, because you're going from doing something mechanically to producing electricity. And the motor is the other way around. I mean, the motors convert electricity into a rotary motion, which is a mechanical motion. And here are some characteristics that you guys can read through on your textbook. Now, this is very important. Okay, the three-phase AC power. Okay, the three-phase AC power has three legs that are 120 degrees out of phase. Out of phase means that they're not basically, they don't go through zeros and their maximums at the same time. See, all three of these waves, they go through zero at different times. So this one goes to zero here, this one goes to zero here, and this one goes to zero here. See, the maximum value is here for that one, is here for that one, and is for this one. So at different times. Okay, so when you have a connection of three phases, three conductors, for example, and three different coils in here, these three lines are out of phase by 180 degrees, and that's what I mean by three-phase AC power. Okay, so the windings may be in the form of a Y or delta. These are the two types of three-phase connection. You can either have it like this. This is called the Y, but because of obvious reasons, right? It looks like the letter Y. Or this is also called the star connection sometimes. And this is called the delta connection. In the Y connection, any pair of terminals is across two coils in series, right? So, and each connection is 120 volts. When you get, sometimes you get three-phase power delivered by the power company to your facility. This is what happened, right? So they connect three different coils like there, and each one of these has 120 volts. So when you measure the voltage across any two terminals, you will get a higher voltage than the 120 voltage. But it's not going, even though they're in series, we cannot just add this one plus this one, for example, and you say you're going to get here 240. And I will explain why not in a few minutes, okay? Whereas the delta connection, you have this connection like that, and then you have three terminals. When you measure the voltage across any two terminals, like AC or AB or BC, you will read the same amount of voltage that is going through this coil right here, okay? Because if you measure the voltage from here to here, it's the same as you measure it from here to here, and you only measuring the voltage across this coil, and that will give you exactly 120 volts in here, okay? Whereas the Y connection, when you do this measurement, when you take the voltage across any two terminals, you will get 208 instead of 220. You have two coils in series, but you don't add them straight like this because you have a phase angle here, okay? So instead, you take the one and you multiply that by a factor of 1.73. Not by the factor of 2, but 1.73. So that will give you 208. So in here you have 120 and 120, but if you take the voltage across these two terminals, the voltage here is going to be 208, and I will explain that in just a minute, okay? And remember, the Y connection measures the voltage across this branch, right? So this is the same thing that you're gonna read over here. So if this is 120, you're gonna measure 120 here. In the delta connection, any pair of terminals is across one generator winding, and the output is 120 for the reasons I just explained, okay? So the other coils are in parallel. So if you take this one, you can see that this and that one will be in parallel. They're parallel branches. So the current capacity of the lines is increased by a factor of 1.3. Okay, in this case, the voltage is, angle. So you multiply one winding times 1.73 and you get a higher voltage here. In here, you get the same voltage, but you can increase the current by a factor of 1.73. That marks the end of the slides for this chapter 15, but I'm going to go ahead and take a minute to explain this why the factor of 1.73 with the three phases, okay? Let's see, for example, here is what we just went over, all right? Three phase, you have the Y connection, you have the delta connection. The Y connection gives you the same voltage that is across the coil at any terminal, right? The Y connection, even though you have 120 plus 120 and these are in series, when you measure it here, you're not going to get 120. Instead, you're going to get 208. You're not going to get 240. You're going to get 208 because you multiply any one of these values by a factor of 1.73. Okay. And the reason why is the following. Okay. You think about it like this. If you have these two coils like this, like in the flat line, okay, so basically there will be no angle, or the angle will be just the opposite of each other. It will be 180 degrees. So if you add, let's say we can think about this as vectors, okay? So if you have this vector and you add these vectors, what you get this whole amount, right? Because it's a straight line. So if you have 120, and you take the measurements between the two terminals, you will get 240 because they're in series and they're like in a straight line. Okay, you can just add this one plus that one and then you get 240. When you have two lines like this and you have a phase angle of 120 degrees, if you were looking at this like vectors, okay, so this vectors goes in this direction right here, and now this other vector will go in this direction right here with the angle of 120 degrees between them. So when you add this vector plus this vector, you're not going to take this one and plus that one. Instead, you're going to take the two ends and you're going to measure this distance right here. And that distance right here is going to be more than 120 but less than the sum of these two. Okay, so this one will be 120 times a factor of 1.73, and that will give you 128. Okay, remember, on the delta connection, you measure from here to here and you get the same 120. Okay, but it's only one coil right here. Okay, now, where this 173 came from? Let's see if you guys remember from your tree class back in high school or back in previous classes that you took in college. There is something that is called the law of sines. The law of sines says that if you have a triangle and you know the magnitude of the sides and you know the angles in between them, you can always say that every side divided by the sine of its opposite angle, okay, is equals to the other side divided by its angle, which is equal to the third side divided by this angle. So if I'm looking, what's this distance right here, what this magnitude right here, and I know this one and that one, and I know I know their opposite angles as well, I can find this just like applying this equation, okay, using two of these factors on this equation. Let's see right here, okay. In here, I know that I have 120 volts this way. I have 120 volts on this other line right here, all right? So I need to find out what is the sum of these two. So because they are 120 degrees out of phase, or the phase angle is 120 degrees, and you applying the law of sine, I can say that C divided by the sine of 120 degrees must be equals to any one of these sides divided by the sine of its opposite angle. So let's take this one right here. So this one should be equals to 120, which is this magnitude right here, divided by the sine of the angle that's opposite to this side, which is this one right here, 30 degrees. Okay, so that would be this one divided by the sine of this angle. It has to be equals to this one divided by the sine of this angle. All right. And if I solve this equation for C, I end up that C equals 120, which is this right here, times the sine of 120 degrees divided by the sine of 30 degrees. This expression right here is equals to 1.73, and that's where the 1.73 came from. All right, so now if I have 120 volts this way and 120 volts this way with 120 degrees angle, I can take the measurement from here to here the same way that we are doing here on this one right here. I can take the measurement between any of the two terminals, AB, AC, or C or CB, and I will get 208 volts. I'm not gonna get 120 plus 120 because of the phase angle. Okay, and how do I know that this is 30 degrees and 30 degrees here? Because remember, every triangle has 180 degrees within. The sum of all angles must add up to 180 degrees. I already know that this is 120, so I only have 60 more degrees to split, and because this one is 120 and that one is 120, so in other words, these two sides are equal in magnitude, so I can just split the 60 degree in 30 and 30. Okay, so but this is where the 173 comes from. Now just remember, when you have three-phase, when you're working with three-phase power, if you use the Y connection, you're gonna multiply the voltage on the windings times 1.73, and that would give you the voltage across any two terminals. Where in the delta connection, the voltage would be the same as the voltage across the elements right there, because it's just taking the measurement from here to here is the same as taking it from here to here. Okay, and the current on this one though is gonna be higher by a factor of 1.73 as well. All right, so with that being said, this is the end of chapter 15, and I hope you guys enjoy it. If you have any questions, please do not hesitate in letting me know, okay, so I can assist you. As always, thank you for your attention and the opportunity to serve you, okay. We'll see you on the next video.